So we talked about quadratic resistance versus regular resistance when we were talking about fluid resistances. So think about it this way. So when you have a laminar flow, it is usually what we call a steady flow. And this is usually when force varies as v. Force is a function of velocity. When it is turbulent flow, in this case, the force will vary as v squared.
Yeah. Velocity or volume?
Velocity. Good point. I should be more careful. I should do the funny looking one, right? That's velocity. Good point. Thank you. So think about it this way. When smoke rises, it goes like this for a little bit. And then what does it do? So it goes steady for a little while. And then it becomes turbulent. So I can't tell you much about turbulent flow. I can tell you the velocity where any flow becomes turbulent. We can calculate that. It's called critical velocity. And that's the transition. A certain velocity needs to be reached before any flow becomes turbulent. And that's the velocity we can calculate. And guess how we do that? There's one thing, one of my favorite things that comes to our rescue. Starts with a D. Dimensional analysis. So let's do that really quickly. So first of all, I want you to figure out why does turbulent flow happen? So that's question one to answer. So we'll do question one, which is why. And then we'll do the at what speed, right? So why does it happen? It happens mainly because of velocity and pressure differences. So here's what we're going to do. Resistive force in turbulent motion. So I'm going to tell you that that force is being caused by cross-sectional area. We'll call it A. It's being caused by the velocity of the object with respect to the fluid. And 3, it's being caused by the density of the fluid. Rho. Can you come up with a formula? The answer is yes. All we have to do is do a little bit of dimensional analysis. So may I write this as A to the power alpha, V to the power, and rho to the power. So that's my equation A. This is where everything will get plugged in at the end. What are the dimensions of force? mL t to the minus 4, right? Newtons are kilograms meters per second squared. That's the dimensions of force. And what are the dimensions of A? Area. What are the dimensions for V? And what are the dimensions for rho?
Wouldn't it be 2 alpha area? I mean, 2 alpha. Yeah.
Oh, yes, you're right. It should be 2 alpha. Good catch. And then this would be minus 3 gamma. Make sure I don't mess up. Then I can do a L 2 alpha plus beta minus 3 gamma, M and T. And on this side, I'll have M to the power 1, L to the power 1, T to the power minus 2. So now I can compare powers or evaluate powers. So M will be just 1 equals gamma. L will be 1 equals 2 alpha plus beta minus 3 gamma. And T will just be minus 2 equals minus B. So what do I get for beta? 2. What do I get for gamma? 1. What do I get for alpha? Plug all of these back into equation A. The resistive force will be proportional to A to the power 1, B to the power 2, and rho to the power 1. How do I get rid of the proportionality? I put a constant there. And that constant is very important. That constant depends on the object itself that's moving through the fluid. Remember we talked about this, that beta in the resistive forces was also dependent on the thing that was moving through the fluid before? Last chapter, last week. That K also depends on the fluid itself. So K depends on the shape of the moving object. And I'll give you 2 values of K. For a flat disk, K is 0.7. And for a pear-shaped object, K is 0.3. Another important thing that you should have seen from here is this force is proportional to speed squared. So what's kind of a drag? Linear or quadratic? Quadratic.